What I hold here in my hand is a heat exchanger. It's a shell and tube heat exchanger. Now when I show up to class, I'm going to show you this in person, and we're going to take it apart and look at what's inside. And that's pretty heavy, so I'm going to put it down. But that's a miniature shell and tube heat exchanger. Most shell and tube heat exchangers that you see in industry will be an order of magnitude larger than that. But basically, these are devices that are used to raise the temperature of a fluid before it enters a process, or used for energy harvesting of that thermal energy. So the point of this class is going to be to learn how to look at a problem like that, look at a system, and basically to, number one, be able to identify and state correctly the heat transfer problem. Number two, be able to learn how to make good assumptions about the heat transfer problem and check them. And then our third learning objective for this class will be to learn how to solve heat transfer problems with both rigorous analysis and by making quick conclusions derived from an understanding of the fundamental concepts. So let's begin. The first question is, what is heat transfer? Heat transfer is an extension of thermodynamics, but it's different. Thermodynamics deals with systems in equilibrium, where heat transfer inherently deals with non-equilibrium systems. So our definition is that heat transfer is the movement of thermal energy caused by a temperature difference within a medium or between media. So what we're saying is that heat transfer is a non-equilibrium process. It's driven by temperature differences between two bodies or within a body. I'll give you a moment to write that down. So let's move on. Let's look further at the relation of heat transfer to thermodynamics. Relation to thermodynamics. So in thermodynamics, we worked with having a system that was at one state, state 1, temperature 1. And we were concerned with what this system looked like after some input moving to state 2. So this input is some sort of process. It can be work added to the system in the form of heat, mechanical work, so on. But in thermo, we ignored this process. We just looked at state 1 and state 2. We treated this process like a black box. So here in heat transfer, we're going to open up this black box Because we're concerned with non-equilibrium processes. We're concerned with what happened between state 1 and state 2. What caused the temperature to move from state 1 to state 2. Those processes are characterized by heat transfer. So, heat transfer is a non-equilibrium process. Otherwise said, temperature gradients or differences of temperature exist in the system while heat is transferred to move the system from state 1 to state 2. Meaning that the system we had on the board before, the box, when it's moving from state 1 to 2, as it changes, its temperature changes from temperature at state 1 in a process that's non-equilibrium, meaning some part of the system may still be at temperature 1, while other parts of the system are changing towards temperature 2. And those differences in temperature during that transient process characterize heat transfer. So the degree of heat transfer is related to the degree of non-equilibrium, thermal non-equilibrium in the system. So the next question is, how is the heat transferred? How do we characterize that black box, the process of heat being transferred? So we're going to ask a lot of questions today, because it's the first day we want to introduce ourselves to this new material. How is heat being transferred? Or basically, what are the mechanisms by which thermal energy enters or leaves a system to move it from state 1 to state 2? So we have three basic modes of heat transfer that describe this. Three modes. Maybe some of you already know a couple of them or all three of them. If you've read chapter 1 already, then you're familiar with the three. But here they are for you. The first is conduction. So conduction, I like to talk and introduce these subjects, these three modes, these rate equations or rate concepts, in personal terms. So conduction is like a handshake. It's literally like